Thank you so much for spending your morning with me. I look forward to spending the next hour and 15 minutes with you and talking about math and core math instruction. I'm going to start off by sharing my screen and the PowerPoint. Okay. One moment, we'll get this up. Um, Sorry, I should have had this open at the time. But there we go. Okay. On this first slide, I kind of share the abstract, what I said I was going to talk about because I want to be crystal clear and make sure that you know what we're going to be doing for the next hour and a half and make sure that it's relevant for you. So that's one of my goals for today is to make sure that when you leave this session, you have something to think about and do and kind of action items for your core math instruction and to support students with and without disabilities in your classroom. Okay. Our agenda for today, we're going to briefly kind of talk about the current state of math instruction. I'm going to spend the majority of the time talking about 6 strong instructional practices. And then I'm going to give you examples. And this is actually going to kind of be embedded throughout it, is kind of how to apply this with ease within what you're doing. Okay. So how do we get here? There are, and I'm not going to go through all of these panels and boards and publications, but what I really want to share on this slide is there are a lot of things and publications and interest around math and math instruction and what math instruction should look like and sound like and what students should be doing and what teachers should be doing. And there are strengths from all of these. I am not going to subscribe to the math wars and say we need inquiry versus explicit instruction. The stance that I come from is really kind of learning from everywhere we've come in this math progress and identifying what works for whom under what conditions. And even Anita Archer, who is like the queen of explicit instruction, says it's not or we shouldn't be doing explicit instruction or inquiry-based instruction, but we should be doing and when. And the 6 components that I'm going to share with you today really stem from substantial research and a publication from the IES Practice Guide that says, hey, we have a lot of evidence showing that this kind of instruction works for the majority of kids. So when we're thinking about what works for whom under what conditions, this has a really good chance of being helpful and effective for students. But as you all know, you also have the classroom level. So when individualizing and when looking at, well, what works for whom under what conditions, there's a lot of things that play into that. Here I have this kind of general roadmap. My goal for this slide is that you really just think about where students in your classroom are in their math learning process. And each student in one classroom, whether it be a general education classroom or a special education classroom, may be at a different point. For some students, they're really looking at acquisition and they're really thinking about, well, this is the first time I've seen this and I'm making sense of this and I'm making sense of the concepts and the procedures that accompany those concepts. Or you have proficiency where you're really starting to practice and building for accuracy into fluency, where you're able to do it with greater ease and accuracy, and generalization and maintenance. So you're able to maintain these skills, these concepts, and situate them in new situations and novel situations. So again, within the classroom, students may be at different points. And it's also something, it's interesting to consider that even for an individual student, when you're talking about different topics, they may be at different points, which again goes back to what works for whom under what conditions. Okay. And it's exciting because that's also where your expertise as educators come in. And you're like, okay, I have this wealth of knowledge and I know my students, so I'm able to make these instructional decisions, whether it be at that core level or you're talking about kind of more of that tier two or tier three intervention. Now, what I'm going to share with you today comes from the IES practice guide, and they identified six kind of foundational things that have a lot of research and application and support for students with challenges learning mathematics in the elementary grades. Now, if you're a secondary teacher watching this, these actually also apply to secondary classrooms. So don't think this is just elementary. We just adapted up to secondary mathematics topics. Okay. So I'm going to go through each of these elements and we're really going to unpack these elements. As we do this, one of the things I want you to think about is how does this apply to me in my classroom, in my curriculum? One of the questions I get a lot is, well, what is the best curriculum? We're changing curriculums or we're doing a curriculum evaluation. What is the best curriculum? And I don't have an answer for the best curriculum. I think all curriculums have strengths, all curriculums have limitations. And I think one of the things that we can do as educators and experts in the field is really consider, okay, what are the strengths? What does this program that I've either chosen to do in my classroom or I'm being told to do in my classroom, what are the strengths that it brings? What are the areas that maybe I can adapt or provide overlays or strengthen with supplemental material? So as I go through these, I want you to kind of think about that. Well, how does this apply or what does this look like in what I'm doing in my math classroom? Okay. And with that, how might I kind of improve or supplement what is happening so that I am meeting my students' needs? I will make sure that that we share this practice guide as well because this is a wealth of information. We're in the next hour, we are just going to kind of like touch the surface of what you can learn on these topics. Okay. So the first recommendation is systematic instruction. And over the next few slides, I'm going to unpack each of these and give examples. So I'm not going to read these to you, but I will let you kind of read them yourself and come back to them as well. One of the things I do want to note is that you're going to see elements of these throughout the other recommendations as well. So there aren't really any silos, like this is specifically this, but you're going to see how systematic instruction can be seen in the elements. For example, number 4 on there is provide visual and verbal supports. And we're going to see that in the representation suggestion as well as the language suggestion. Okay. Another thing I think I really need to kind of address right now is what systematic and specifically explicit instruction is not, because there's a lot of misinformation around explicit instruction and systematic instruction. And again, I don't give credit to the math wars. It's really, it's not or, it's when. And one of the criticisms of explicit instruction is that I've heard it is just mimicking. It's students mimicking the teacher. The teacher says something, the students repeat it. It's mirroring, it's boring, it's teacher-centered. And quite honestly, I think systematic instruction is none of these when done well. So I just wanted to address the elephant in the room and kind of say, hey, when done well, explicit instruction is not just the student mimicking the teacher. Another thing to note is it's not just the teacher lecturing. When done well, systematic and explicit instruction is really student-centered because we're making systematic and pre-planned and real-time decisions in the classroom based on the student and the student need and how the student is responding to and receiving the instruction and engaging in the instruction as well, which you'll see in a few slides. So one of the points in the IES practice guide is that systematic instruction involves review and integration of previously learned skills. This is not spiral curriculum. This is mastery and then readdressing. Because remember on that little roadmap, we had generalization and maintenance. And in order to make sure that we're maintaining this generalization and maintenance, we need to continue to go back and review, and not just review, but also reteach. If you listen to Paul Riccomini's in presentation yesterday morning, he talked about spaced learning over time and kind of how we need to make sure that we recognize how students are learning and reteach. So systematic instruction involves reviewing and integrating information. It also um, includes that within the lesson. As you see here, I have this kind of model of a lesson where we have that conspicuous review. So when thinking about your curriculum and how you're teaching, are you starting off your lesson or starting off your new content, kind of priming students' previously learned information, pulling that to their conscious so that you have that in your conscious and you can easily access, or that information I should say is easily accessible so that we can apply it to the instruction. And then also we have the modeling, which again is not teacher lecturing, it's not students mimicking or mirroring what the teacher is saying. It is really engaging in the doing process. You have metacognitive talk, you have examples and non-examples where you're setting the parameters of what's happening in the concepts and the procedures. Also, throughout this, you have practice feedback, and then that slope from guided practice to independent practice, which again has all that feedback in it so that you get to the point where you're confident that students can do this independently and understand the concepts independently. Okay. The second point that they had there was when introducing new concepts and procedures, make sure the numbers are accessible. So the example I have here, when learning to subtract with regrouping, which example would you use first? And I think it's pretty obviously here. You would use the first one. You would use A, 12 minus 8, as opposed to B, which I'm not even going to attempt to, in this time, read that number in a Zoom where it's being recorded because I will mess up. Um, so anyway, so it's an obvious example of using easily accessible numbers, which goes back to that priming and having that information in your working memory and being able to kind of easily access that information. The other example I have here is when learning word problem schemas, which I think there are other presentations about that. Which example would you use first? This one's a little more difficult. But if we think about making the numbers accessible, the first one I would do is B. I would start with that example. And for the reason that it doesn't include fractions. Fractions tend to like scare students away. So when thinking about new concepts that you're introducing, I think it's really important to make sure that we think about, well, what is the objective of my lesson? If the objective of my lesson is that students are learning the schemas, if they're learning kind of how to do this and how to apply this, you want to make sure that the numbers and the examples you use are accessible. Use accessible numbers, use accessible language. Like I've done a math writing intervention before, and the first time we piloted it, we taught students how to write mathematically, so how to read a word problem and solve and explain. And the first time I did it, we used grade level problems, and it was so challenging because the students were trying to make sense of the math and the writing procedures and the expressive language at the same time. And so we said, hey, this is too much. We then started using problems that the students had already mastered so that they could focus that cognitive energy on the new task. So that's kind of what's happening here with this recommendation. In order to make sure students are making sense of the new concepts, we can reduce that cognitive load with the numbers and the examples that we use. And your curriculum may already do that. And if not, that's a way that you can supplement. Hey, the curriculum used this example, but I think I need to alter that slightly to make it a little more accessible for my students. Okay. The next example, students, to make sure that learning is sequenced and that you're using more or you're starting with easier concepts and learning builds incrementally. And especially to an elementary school audience, I think this is really important when talking about algebra. And if there's any kindergarten teachers out there, you might be like, I'm not teaching algebra, but you are. The fundamental skills that you're teaching in mathematics, even in kindergarten and first grade and second grade, are so important to that secondary mathematics. So building that number sense and these skills early on is important, and making sure that your curriculum is sequential and builds on those skills. Okay. Next is to provide visual and verbal supports. And we're going to see this again later on, but I have an example for you here. And it's funny because I have fractions in here. And I just said, don't start with the fractions if that's going to be most challenging. So we have the problem here. 3.5 divided by 1/4. And if you were taught like I was taught to flip and multiply across, right? But that doesn't really support the concept. So traditionally, we're taught to flip and multiply, but if you think about how visual and verbal supports help mathematical understanding and help students build the concept, okay? So if I read this problem, 3.5 divided into 1/4 parts, what I want to know is how many 1/4 parts are in 3.5. Okay, so even just the language that I'm using when saying this out loud, and rewording it in such a way helps me understand the concept. Okay, how many 1/4 parts are in 3.5? And then if we have that visual support as well, so here I have 4 rectangles, 3.5 rectangles are blue. And then I've divided each of them into 1/4 part to see how many 1/4 parts are in 3.5. Okay. When thinking about your curriculum, how does your curriculum and how do you as a teacher use these visual and verbal supports to help students make sense of mathematics? The next example under systematic instruction is to provide immediate and supportive feedback to students. So here I have kind of this cycle. And if you start with that share, and this is the cycle that when I'm teaching students, my students, or when I'm teaching my undergraduates or my graduate students about modeling in that modeling part of explicit instruction. I talk about this cycle. Modeling should not be lecture. You should be sharing a piece of information, asking a question, listening for students' response, monitoring this response, providing feedback, and then sharing another piece of information or another tidbit, asking a question. And it's not specifically, it's not so scripted that it's one sentence, one question, response is always the same, verbal response, say something, but it can change. You might be sharing a little like nugget of information. You may be sharing a slightly larger nugget of information. Your questions may be an oral question where students have to respond in a choral response, or maybe it's a visual response. I knew having my things here would be helpful. I love using products like these and having students write the response and show me, because then I can look across and see students' responses and provide immediate feedback. Okay. On that explicit instruction, I did want to kind of highlight 2 different presentations. Later today, Zach is going to be talking about explicit instruction. So if you want to learn more about explicit instruction, and then actually right now he's doing the science and modeling and examples, but you can watch that at a later date because you're here with me. The next topic I want to talk about is mathematical language, but I'm going to pause here for a second kind of let you think about that systematic instruction, see if there are any questions that you have about systematic instruction in application to your school, your classroom, your students. Give you a chance to read this slide, and then we'll move on. Again, if you have questions, feel free to drop them in the chat. Okay. Um, Next, we're going to talk about mathematical language. And this is I have to say, this is probably my absolute favorite. I love thinking about how the language we use, whether it be written language, oral language, expressive, receptive, kind of influence learning mathematics. Okay. So IES shares 3 recommendations, and I'm going to talk about each of these and provide examples and explicit things that you can do in the classroom as well. Situating mathematics vocabulary. Why are we talking about it? So this chart comes from work from Sarah Powell, and she looked at math vocabulary across grade levels. So these are the math vocabulary that were in curriculum texts. So at the end of the textbook, you have that index, all of these words students should know, and there are a lot of them. Okay, in 6th grade, we have over 550 words that we expect students to know. Okay, so there's a lot. Next thing I want you to consider is not only do we have a lot of words, but there are different types of words. So this is a little activity. Feel free to grab a piece of paper, just do this mentally. There are 4 different kind of categories of math terms. There may be a literature that says there are others or kind of break these down, but here's just 4 overall math categories for language. And I want you to take a look at how these words fit into those. So you have the technical terms, which are uniquely math terms. You're going to see these in math class. You're going to see these maybe in engineering class, but you're really not going to see them outside of that. You have sub-technical terms, which includes both a math definition and a general language definition. You have symbolic words. So we have not only in our mathematical language do we have words that we typically see kind of in the English language, but we have symbols that mean things. We have numbers that mean something. So we have a whole bunch of different squiggles that have meaning. And then you have general language, things that don't necessarily have a specific math term, but are really important in understanding mathematics. Okay, now that I've given you a moment, here we go. Quick story. So if you look at the general language withdraw, I was working one-on-one with a student one time, and we were doing addition and subtraction with decimals. And she was doing great. And we came to a word problem, and she's like, I don't know how to do this. And of course, I was like, yes, you do. You can do this. We've been working on it all week. You've got this. And she's like, no, I don't know what deposited means or withdrew. And I was like, oh, it was the language that was the barrier for her understanding and doing this mathematics. And it wasn't even technical math language. It was just this general language that has meaning in mathematics. So as teachers, we should be aware of language as a whole, how language is used in the curriculum, and how language is taught in the curriculum. Okay? Which brings us to another layer of language. See, this is why it's my favorite. It's so complex and we can just kind of unpack it. So when thinking about the language of mathematics, we have both expressive and receptive language. Okay, I'm doing a lot of expressive language right now, and you're doing a lot of receptive language. So with the expressive, we have speaking, we have writing, and then the receptive, we have that listening and reading. And in general, receptive is kind of what develops first. So listening to terms and understanding their meaning, or reading a term and understanding their meaning, is going to develop faster than that expressive, being comfortable speaking or writing. I'm sure that you can think of a term that you're like, oh yeah, if I read it, I know what it means, because you're using context clues, all of that. Or if I hear somebody say that, I understand the meaning of it, but I don't quite feel comfortable using it in my own discourse, in my own speaking or writing. So it develops at different rates. Okay. So we have these words that develop at different rates. And you can be within your classroom, you can have students that have different levels of understanding of these mathematical terms and different levels of being familiar with and comfortable with receptive or expressive language. Okay. So one thing we need to consider, and I think there's some presentations that Patton has in this conference as well about the math language. I think Sarah Cox is doing one, is to teach math vocabulary. Now you can't teach it all. Remember, I showed you that slide with all, like that chart with all the numbers of math terms that we expect students to know. You can't teach it all, but we can think about, well, what terms do students need to know to be successful? And what terms have the most utility, potentially maybe most challenging for students? And then from that, how am I going to teach it? Oh, there we go, Sarah. It's right out there on the slide. Sarah's doing one on graphic organizers. Okay, so you should check that out as well. And one thing to do is the Freyer model. Before I kind of dive into the parts of the Freyer model, I do want to say that when teaching math vocabulary, another thing to consider is, well, when do I teach it? Do I need to teach it before? Is this a word, a term, a concept that students really need kind of going into the lesson? Is it a term that I can teach and develop and unpack during the lesson? Is it a word that I didn't anticipate students would need instruction on, but here we are in the lesson, and I really need to kind of develop their understanding and parameter around this term and concept? Or is it something that I need to review afterwards? So when the instruction happens, can change based on the term, based on the students, based on the utility. Okay. Another thing is when thinking about teaching math terms, we're not just teaching the term. In fact, I would say, and I've said this before, but now it's going to be recorded, the technical definition of the math term is the least important part of it. Okay, when teaching vocabulary, the technical definition is the least important. Okay, the definition that is in that back of the math book, not the most important. Okay, what is the most important is understanding the term, how it's applied, and the parameters around it. So this is what the Freyer model does, which I love. You start with the word. Okay, I'm going to go back a slide a second so you can kind of just see that now that you've seen the next slide and some of my bullets here disappear. Okay, you start with the term. Students should be able to say the term, hear the term, be that familiar. Remember that expressive receptive. Like we want students to have that expressive and receptive understanding of the term itself. And then I would recommend you move to the examples. Okay. This is not set in stone. If you want to start with facts and characteristics, that's fine. But what I recommend is that you start with the easiest accessible point for students. Okay. What do students know about this term, this concept? And examples is usually an easy way to start. It's easily accessible. You can use pictures, you can use terms. It doesn't have to be complete sentences. It doesn't have that technical jargon of the definition in the back of the book. So you start with the examples. Then go to the non-examples. So this is the examples are this is the term. The non-examples help students set the parameters around that. This is not the term. This is when that term doesn't apply. Okay, so you're starting to develop the understanding of the concept through these examples and non-examples. And then from those examples and non-examples, you can come up with a list of facts and characteristics. Okay, so we have our examples, we have our non-examples. These characteristics are going to be the salient, really important parts of this term and concept. And from that, we can then create a definition. And I would start with a student-friendly definition. Okay, have the students put it in their own terms, their own language, so that they can access this word and this concept. And then if you want, if you have time, have them copy that definition that is in the glossary and compare. Do we have all the salient features in your definition that the book has as well? Yeah. And what's nice about this is that, again, it builds that concept of the word when we use it, when we don't use it, setting those parameters around the term. Okay, and it's not just memorizing a definition. Another thing for you to consider in both your curriculum and kind of daily language and mathematics is making sure that we're using clear, concise, and correct mathematical language. I have links here to two articles that I wrote with Elizabeth Stevens and Sarah Powell about math language. And in these, there are tables that say, instead of this word, use this word. So for example, instead of reduce, because we don't reduce when working with fractions, you can say simplify or reword or things like that. Okay. I'm not going to I could talk all day about this, but for sake of time, I'm going to move on. Here's an example of that table. So you will have access to that through those QR codes. Next, so we've said use language, teach the language, and now we're talking about supporting students' expressive language. So having opportunities in your math class, in your curriculum for students to use this language in discourse. And I'm going to provide 3 examples of ways for students to have verbal and written explanations of problem solving. And all of these are kind of prompted reasoning tasks. Okay. The first is a prompted writing task. What I love about this is my little cloud bubbles here, my little examples, you can apply this to any part of your curriculum, like any curriculum you have. If there is a solve and explain, or if there's an opportunity for students to have that expressive language and use that discourse, you can use a little label sticker and you can print out label stickers and have them use these words. Or you can put a little post-it note on students' papers. So if they have their worksheet in front of them, you can put a little post-it note that says, use these words in your language. You can have it on the board. If you're using a post-it note, this is a great way to differentiate, because you may say, okay, this student, I want them to use these terms. This student, I'm going to scaffold a bit more. I want them to use these terms, or I have the term and kind of a picture or definition or something to prompt their memory. The point of these activities are to reduce the language load, because again, remember that expressive language is more difficult than receptive. So we're reducing that cognitive load for them to recall and use the language, and we're scaffolding it. So we're saying, here are the terms that we want you to use, and having students apply them accurately and become more comfortable using them in their writing and in their speech. Okay, so there's a lot of ways that you can differentiate and apply this to your classroom. And again, what I love is it can be an easy overlay for your existing curriculum with a simple use of post-it notes or those little labels. Okay. Another way that you can support that expressive language is through worked examples. So a worked example is essentially an example that has been solved for you. Okay. You can see here, this is an algebra example that I work a lot with, like secondary teachers in algebra and how to scaffold with algebra. So here in the worked example, in that green arrow, we've given the directions and we've given the equation. Now, if you have an equation and students need to solve it, or if you have any kind of math problem, students need to solve it, if you're continuing to talk and be like, hey, let's unpack this, students are already kind of like going and trying to solve it and do these things. We don't want that when we're working in this worked example problem. Okay, so we give the problem. That orange arrow shows that we want students to study the steps for how the equation is solved. For each step, we want to think about what has been done and why it works. Now, again, if you just have the problem there and students need to solve it, they're not thinking about what and why. They're just trying to get to that answer. Okay? Which is where that blue arrow comes in, and we've solved the problem for them. Into the pink arrow. There's your answer. You do not need to put that cognitive energy into solving the problem, which goes back to my orange arrow. We want to draw that attention and that energy to thinking about what happened and why. And in this example, you can see I color coded. Elementary teacher at heart. I love color coding things. Okay. In the instruction piece, I wouldn't just give students the worked example with these instructions and say, it's been solved for you. Think about what's happening and why. This is a great opportunity for you to think about using metacognitive talk, using teacher talk, and modeling how to work through and share that expressive language. Okay. I then also love to include graphic organizers. That's how my brain thinks. So when I put this together, I always think, okay, what and why? Here we have that what column, here we have that why column. What is happening from A to B? Why can we do that? Why is it happening? What is happening from B to C? And having students articulate that. If I wanted to scaffold this using that prompted writing task, I could say, use these terms. Okay, and I can provide some terms that I want them to use in this activity. And then another thing to do is, and this is that math writing intervention I was talking about, is have students write. Have students write about their mathematical reasoning and mathematical understanding and problem solving. And research shows that just having students write improves their understanding and improves their written expression about it. But then what else we did was in this intervention, we said, okay, let's scaffold how they write. So kind of looking at writing research in SRSD and then also the kind of math research, thinking about what we know about good math instruction. We combine this into a way to have students address the problem and think about what's happening in the problem and using a tack strategy to think about, well, what's the important information in the problem? And then drawing a representation, which is one of the things I'm going to get to soon, because drawing representations, we know that students who draw representations are more likely to solve the problem correctly and better explain their reasoning. Interestingly enough, even if they don't get the representation, even if it's not an accurate representation that they've drawn, they're still more likely to solve it and explain it. Okay. And then solving the equation, getting into that writing part, stating what the question was asking, what they did and why they did it, and then concluding the paragraph with the answer and checking their work. So we've kind of unpacked, rather than just solve and explain your work, we have a systematic way for students to solve and explain and unpack what is happening in their math. Okay. So I see that we have 2 questions in the chat. In that, the language part, I really wanted to share with you the recommendations and unpack them in ways that you can immediately apply them to the classroom with your existing curriculum. I'm going to address some of these questions and let you read this representations page, which we'll dive into next. So one of the questions was about the QR codes. Yes, I will make sure everything I share is available. If those weren't working, and if it's not working in the what I've posted, I will share it with Patton and they can send it out. Next, the question about the Frayer model. If using the Frayer model with the whole class, would you post the graphic organizer to refer to or ask students to place it in their notebook? That's a great question. I think this is really one of your what works for whom under what conditions. I've had teachers do it as the poster, like it is a poster in the classroom. We have it in the classroom. We created it together on a poster board and now it's hanging in my classroom. I've had teachers where it is in your notebook. Looking at my kids' math notebooks, it would become a crumpled mess. But for some students, having that there, if you have a notebook like this or like a math notebook, gluing it in the back or having a vocabulary part of your math toolkit might be helpful for some students because then you can just say, hey, go to your book, or we're working on a writing activity. Okay, we're doing discourse, we're doing discussion. Pull out your Freire model and use that, study it for a minute, and then use this language to talk in the classroom. Okay. Somebody also shared they use Google Classroom and has students made slide. I've also seen teachers kind of put it together, and then if you cut out the parts, you can have that as an activity where students have to kind of put the puzzle together. Or if you're having students breaking them into groups, like everyone gets a part of the Freire model, and then you have to find your group of four, and that's how you assign groups for the day. So there's lots of different ways that you can do that. And I love that people are posting things in the comment too, posting their ideas. Um, Melissa, I will say, so you're interested in learning more about this. If you contact Patton or contact me, I can share things. That is something that I developed, but I'm happy to share that. I have scripted lessons and all that kind of stuff. Another question about the writing strategy, the PRISM strategy. Do you think it could be independent? Or do you feel that instant feedback and guided practice is the way to go? Like everything, I think it's scaffolding back. So at first, like and I'm happy to share the lessons that I created, it's modeling. And so it's whole group kind of talking about what makes good math writing. And then we practice each of the parts and you're providing feedback. And then by the time you're putting it all together, we started with peer feedback. So peers were giving each other feedback, and then we went into independent feedback. And then the teachers giving feedback throughout the time. So it is, I think the feedback is scaffolded where you're giving more feedback and more immediate feedback and a greater frequency of feedback at the beginning, and then you scaffold it back, and you have peer feedback or peer writing assignments, and then you're providing feedback as needed. We also have a rubric that goes with it as well. Okay, I'm going to close the chat. Feel free to keep dropping questions in there if you want, but I'm going to move on to representations, which is another, I think, really fun one. So representations are so important at the elementary level. And I think that's one thing I think elementary teachers do really well is use representations in the classroom. And it's kind of just like natural. Yeah, we want kids to be touching math and all that kind of stuff. And once I get to the secondary level, I'm like, hey, students should still be like moving things and manipulating and like making sense of math with manipulatives and objects. So that's sometimes a harder sell, but that's what my next presentation for Patton is going to be this afternoon on using algebra tiles. So diving into representations. Okay. The first example is that to provide students with concrete and semi-concrete representations that effectively represent the concepts or procedures being covered. And I put this as a whole slide because I really wanted to draw attention to both the fact that we're talking about concrete and semi-concrete. And there's different language you may hear in the fields. And I'll talk about that in just a moment, but then also that it effectively represents the concepts or procedures being addressed. Okay. So this is again where your curriculum may have certain examples and certain sets. But as you're using your expertise and you know your students, are the examples and the representations accurately representing the concept for my students? Or are there other ways that help students make sense? For example, let's take a look at 2/5. There's lots of different ways to represent 2/5. And I would probably argue that understanding kind of all of these is the key. And kind of thinking about when to apply these is important. But what you would want to think about is, okay, well, what should I be using when? When does it make sense to use parts of a group or a set and manipulatives that demonstrate that? When does it make sense to use a fraction bar or the number line and draw connections across these? So there's lots of different ways to represent them. And thinking about not only the concept that is being taught and the situation that you're addressing and how to represent that accurately, but also helping students kind of identify which representations to use as well and which ones to make sense of. So kind of flexibility within these. Okay, which then goes into the practice. So when teaching concepts and procedures, we want to make sure that we're connecting concrete, semi-concrete representations to abstract representations. And the word I have here is integrate. So on the next slide, here are different examples of CRA integrated. And I will use myself as an example that when I did my dissertation, when I first started doing research on using manipulatives and representations, I was kind of that mindset, like, we have to use concrete manipulatives. And then the students draw the pictures. And then we have them write using the numbers and the symbols. And it's not that step by step element specifically. It's not like only concrete, only representation, only abstract. Okay, there's actually a lot of research out there and more recent research that is showing that integrating and building this connection across these is important. So this is an example of a worksheet that I created where we worked with word problems. So you have the word problem. I wanted to, in the word problem, identify the operation that you were going to use to solve the problem. And then we used objects. I had them draw the picture, and then they solved it with abstract. And then I had them do the number line as well. Okay, so kind of doing this together at the same time is important. Now, that doesn't mean that every single time you need to use a worksheet like this or a graphic organizer like this. You may start with concrete representations and then introduce having the students draw them. Okay, you may do the concrete representations with the abstract. Here's the number sentence, and here we're gonna to build that. Okay, and then the other picture I have on this slide is Emily Bach using virtual manipulatives. So here's an example from a publication that she has where she used virtual manipulatives. And again, you have the virtual and then the students drawing it and then the abstract sequence. So the big takeaway for this is it's not necessarily step by step, but really thinking about that integration. Okay, so we want to move students to the abstract. We don't want to keep students in that using concrete manipulatives that they can touch and move around. Although that's a really important part when building the concept. Okay. What I like to think about when working with teachers and students on CRA or CSA, it may be called, is that drawing part in the middle. Sometimes I think we want to like start with the manipulatives and then jump to the abstract, but that drawing part in the middle and having students draw the representations is really important because that allows for what I consider self-scaffold, and students can draw the picture if they need to, and then kind of start to self-scaffold away and kind of stop drawing as they no longer need that or want that to help make sense. Also, state testing, I hate to say it, but we have to bring it up. You don't necessarily have manipulatives like my algebra tiles here for state testing, but you have pencil and paper and you can draw it. So if we really have students develop where they can create these visual representations, that's going to be a really important piece. Okay. If you're using virtual manipulatives, here is a site. I don't know if you're familiar with the Toy Theater. It has a lot of virtual manipulatives, so you can check that out. Here is an example from Emily's work again, and what I wanted to share on this site is that language and that discourse that went with the modeling. So here she has a verbal think aloud that goes along with the representation. Okay, and you have this on the slides, so I will kind of let you read that on your own. I'm going to keep moving on for sake of time. Okay. Another thing to consider for representations is being able to use them as thinking tools. So having students think through them. I was working with teachers, high school teachers one time using algebra tiles. And one of the teachers was kind of using them. And he's like, I think differently when I'm moving these around. And it's like, yeah, we do. It kind of makes sense, and it makes sense in a different way. And our mind is really addressing different things and making sense of the mathematics as we're using these manipulatives. So using them as thinking tools helps. One of the ways I like to use them as thinking tools is using them with common errors. Okay. And it's important to make sure that errors are not seen as the like bad, it's bad to make an error, but really kind of unpacking, we all make errors. Um, and it's a natural part of human existence and mathematics and mathematical learning and learning in general. So kind of how do we learn from these errors? So if you look at this, what is the common error that students make? And one of the common errors is adding the numerators and adding the denominators. And this could actually go back to language too, because if we say the top number and bottom number, when we're talking about a fraction, we're reinforcing this whole number properties and applying whole number properties to fractions and rational numbers. And that's not the case. So a fraction itself has a unique place on the number line as opposed to being 1 over 10. It is 1/10 plus 1/2. Using manipulatives to kind of help students think through, okay, why did the student make the mistake? If we said 1/10 plus 1/2 equals 2/12, where did that error happen? And again, it happened because oftentimes we say top number, bottom number, and we're reinforcing these whole number properties, and then students are applying these whole number properties to rational numbers. But if you have the manipulatives, if you're able to kind of play around with this, you can start making sense of this. Okay. And then give students the opportunity to talk through and explain their processing. So here I've compared using toy theater 2/12 to 1/10 and 1/2. And is the equation balanced? Okay, if it's not balanced, well, why? What do you think happened here? Having students really start to articulate and think about this, because this goes into those non-examples as well. Can we set parameters around what we're doing and why and when? Okay, here's an algebra example. And I, if you come to my algebra one in the afternoon, we're going to delve into this one in greater detail. But if you kind of think about this here, using all these tiles, can you create a rectangle? Okay, so you don't really even need to know anything about algebra to really use these tiles. And we have these tiles, or there's virtual manipulatives, and put them into a rectangle. And then once students kind of create them into rectangles, we can talk about, well, what those rectangles are communicating and start to unpack that. So when you put it into a rectangle, here we have this rectangle, which is taking x squared plus 6x plus 8, which I've represented at the bottom there, and really showing what that means and when we're factoring that out. So really it's x plus 4 or x plus 2 times x plus 4. Okay. And then making those connections using double distributive property, and starting to think through those processes. Okay. Another one is to revisit concrete and semi-concrete representations periodically to reinforce and deeper understanding. And this goes into that presentation that Dr. Riccomini did earlier about retaining mathematical knowledge. So when you're going back and watching the videos, you can check that one out. Okay. I'm going to pause here for a second before we jump into number lines, give you a chance to read this, and I'm going to look into the chat. Thank you. Thank you for adding those things. Yes. Excellent. It looks like a lot of people added those virtual manipulatives. I appreciate that. And thank you, Scott. You use these. They have a lot of fun in the classroom. Manipulatives are fun. I will say one of the things I get from teachers is, but they take a lot of time. And yeah, it definitely takes more time to bring out the manipulatives and have students using the manipulatives. But it's time that you're investing into deeper conceptual understanding. Okay, it's time that you're investing into maintenance and retention and generalization. And so it's really an investment of time, and it's a really good investment of time. So yes, it does take longer. You do have to kind of block out that time, but it is an important one. One of the sometimes I see in curriculums or in curricular materials, they'll have the teachers do an example and use manipulatives, but not the students. And it's really important for students to be able to touch the math too and move it around and make sense of the math. So the manipulatives shouldn't just be teacher tools, they should be student tools. One of the things that when working with students, because I go into the classroom and work with our local teachers and work with local students, and I love teaching the lessons. I usually give just a few minutes of playtime. Like, okay, like I know you want to play with these manipulatives, so build something now, and then after that time is up, they are toys, not tools. Tools, not toys. They're definitely tools, not toys. So we adjust, I let them play, and then they're tools, not toys. Okay, and then they become those math tools. So it does take time. It is an investment. Don't skip over the drawing of the representations because that's super important, and that allows scaffolding and also self-scaffolding of students' understanding. And make sure that students are touching the manipulatives, and it's not just the teachers. Okay. I'm gonna check the chat one more time. It is hard because of pacing. Um, I mean, have your admins have your admins come to the patent presentations and watch this too. Um, when manipulatives are used frequently, they start using their novelty, and students understand them as learning tools. That is true. Yeah, they do lose their novelty in the sense that like I don't really want to build a house of this anymore, but they are shifted into that learning tools. And thank you. Yeah, you can also use manipulatives and drawing to guide students' oral language. Absolutely. Going back to that example, the worked example in sometimes when sharing worked examples, I have a column for drawing a picture. So it's okay, what happened? Draw the picture. Why did it happen? I don't know if you can hear my dog in the background. He is whining at the door there. Okay, I'm looking at the time. I have about 15 minutes left. So we're gonna go through the number line semi quickly. Basically, what I have here is number lines are important. Although if you talk to my kids are like, oh, I hate the number line. But the number line has a lot of utility. Okay, so it can be used across concepts and really help with understanding. The practice guide, this is going to be one of those places where I just say, go to the practice guide. The practice guide has so many examples of how to use the number lines to teach different concepts. So if there's a concept that you're not super confident about, if you go to that practice guide, they're going to kind of show you different ways to do that. Okay. Um, they can be used for whole numbers, for rational numbers. It really has utility, yeah, across concepts. Okay. Word problems. So Word problems are such a fun one. Um, and when done well, they incorporate a lot of the things that we've already talked about. So one of the things to note is that it's important to teach students to understand the word problems rather than just trying to look for quick fixes to solve the word problem. Okay. Um, you can read the kind of what the recommendations are here, and we're going to unpack it in different ways. Okay, the first one is it is not effective to teach keywords. Okay, it is effective to teach problem structure and schema. And I did a quick search, this was probably like a year ago at this point, on Teachers Pay Teachers, and I used keywords and math, and I came up with over 6,000 resources on how to use keywords. And then I did searches on problem structure and schema, and I came up with only 2,000. So there is a lot out there saying use keywords. And I get it. I totally get it as a teacher because we want to make things kind of easier for our students and we want to scaffold that, but it doesn't have long-term effectiveness. It might be like a quick band-aid for your grade level and your lesson and that problem, but it doesn't have long-term effectiveness. Okay. What does, replacing that teaching the keyword behavior, is connecting to schemas and understanding what's happening. And one thing I want to clarify on this slide is when we talk about keywords, like there are words that are important in word problems. There are words that carry that mathematical meaning, that really kind of communicate things mathematically in the word problem. So there are key words in the word problem. What is ineffective is saying, if you see this, then you do this. So making that if then is not effective. Okay. And this is what I mean by that. Okay. When you see the word fewer, you know to subtract. Now notice I have that little red mark down at the bottom. This is not true. Do not teach this. Okay. But if you were teaching keywords, if I was teaching keywords and I said, when you see the word fewer, subtract. Okay, so students are learning, fewer, subtract. Got it. Okay. And then I use this problem. Sarah ran 7 miles yesterday. Alex ran 3 fewer miles than Sarah. How many miles did Alex run? And I know fewer means subtract. And I also know, this is also not true, but this is a rule that expires, that I take the bigger number and I subtract the smaller number. So 7 minus 3 equals 4. My answer is 4. And guess what? It's correct. Pat myself on the back. However, the next day, or maybe it was on that test, that end of year assessment, I encountered this one. Sarah ran 7 miles yesterday. She ran 3 fewer miles yesterday than she did today. How many miles did Sarah run today? And if I apply what I did to the last problem, I say 7 minus 3 equals 4. She ran 4 miles. Okay? But if I read the problem and understand and make sense of the problem, I see 7 plus 3 equals 10, and she ran 10 miles. So again, work from Sarah Powell for single-step word problems. And both of those examples I shared with you were single-step. Keywords led to the correct solution between 26 to 81% of the time, with the median being 57. So here we have flip of a coin if that keyword strategy, if then, is going to work. But then we get to multi-step problems. Okay. And we have multi-step problems. The keyword strategy led to the correct solution between 0 to 29% of the time, with the median being 5% of the time. Okay. So if we're teaching this, it may work in the short term, but it's not going to work in the long term. It's really setting our students up for failure. So what we can do, that replacement behavior, is teaching schema. Okay, and you're going to hear like different people talk about schema in different ways. They may have different words that talk about it, but essentially it's teaching students to understand what's happening in the problem and understand the story type. Okay, and then having students draw a way to organize the problem. So there's 3 reasons why we add or subtract. We're either combining, we're changing, or we're comparing. And there's research out there that using hand gestures helps, especially with the little kids. So you combine, you change, or you compare. So you're teaching students not to look for a word and connect it to addition and subtraction, but looking for what's happening in this story. I think another challenge we have when we talk about word problems, we're talking about problems, like word problems. We've put the word problem in this. And problems can be problematic. I like to call them word stories because we like stories. We like hearing stories. We like reading and listening to stories. And so if you're understanding the story, if you're understanding kind of like the plot of the story, you can then make sense of it. So teaching students to understand what's happening in the story and then use that information to set up the problem. Okay, so there's 3 reasons why we add or subtract. And then, and here you have examples of the different schema, when it occurs, and sample problems. Addressing the schema also allows you to identify that the missing number can be anywhere in the problem. So once you understand what's happening in the story, you use that information to set up the problem, and you use the information from the story to fill in the problem, and then you solve your equation. Okay. There's different attack strategies, and some of the research I've been doing, we use the wrap or the attack strategy wrap. Read the story, analyze the problem, and plan a solution strategy. And then there you see different ways that we've set up the attack strategy in the plan. So if you figured out it's a combined problem, you know that you're going to have different groups and they come together. And you know, based on that graphic organizer there, you have group A, group B, and total. You may then have group A, group B, group C, group D, and total. But you have these groups and they have the same value as the total. In a change, you have a starting value that either increases or decreases over time, and then you have an ending value. And then in comparing, you have a greater value, you have a lesser value, and the difference between those two values. And so you can see how those graphic organizers are set up. And then once you have that, once you've planned your strategy, you fill in the information that you have, which helps you set up the equation. Okay. Here's an example of, I went into Dr. Titus's classroom and worked with her students. And so we talked about her classroom library. And in her classroom library, she has fiction books and nonfiction books, and she has all the books in her library. And so we talked about, well, what's happening in the story here? And we decided that it was a combine because you had 2 different groups that came together to create the total. And if you notice, I don't have any numbers in this word problem. And that is intentional, which goes back to kind of that first example we talked about using accessible numbers. Here, I'm not using any numbers. I don't want students to focus on the numbers. I want them to focus on the content of the story. So this is my entry point into teaching schemas. Okay, working on focusing on what's happening in the story and not being distracted by the numbers and trying to solve the problem. My next scaffold would be to have kind of easier numbers in here and also have the answer. But here we set it up. Fiction books, nonfiction books, all the books. And then we talk about how fiction books and nonfiction books have the same value as all the books. Okay. On this slide here, it says is the same. I have since creating this slide originally changed my language. It's not the same. It has the same value, the same magnitude, but not the same. Okay. Here's an example of a combined story that we talked about. Here, this one doesn't have any numbers in it either. And then here are different ways that we have, I'm showing schemas in different ways. In this one, you can see that the value is in different places. For sake of time, I'm going to continue on, but you have all these slides. Okay, 3 reasons why we multiply and divide. Equal groups, the key components. So we have a number of group and a number in each group, and then we have the total. Okay, here I've given you the answer So you don't have to solve the problem. We just kind of need to make sense of what's happening in the problem. We also have multiple comparison where you have a set times a number of times. So a set number times a number of times, get your product. It's multiple comparison, and then ratio proportion where you have a relationship between A and B, then C and D, and then we're really finding out what happens in that relationship. Okay. Today 215, although I'm also doing one at 215, but here's one that kind of talks about that language and that IES practice guides and talking about attack word problems. So if you want to learn more about that, here's a good one. Okay, I've got 5 minutes left, and we're going to talk about timed activities really quickly. So timed activities, love them or hate them, but they are important, okay? One of the things I want us to leave here today is defining fluency. Is fluency speed and automaticity? I would say no. I say we sometimes confuse it with speed and automaticity, but when we're thinking speed and automaticity, you're like that. I mean, I'm getting a little anxious thinking about that speed and automaticity. Rather than thinking about speed and automaticity, let's think about ease and accuracy. Okay? And when we're thinking about ease and accuracy, you have fact fluency, you have procedural fluency, you have strategy fluency. There's a lot of ways that we can apply ease and accuracy. Brian Ponce is doing one again. And if you don't catch mine at 215 on algebra tiles, if that's not up your alley, you can watch it at a later date. But he's going to talk about fluency, and Dr. Ponce is a wealth of information in this. Okay. How you approach fluency matters. Here's an example of Morningside math facts that I've used before. And I want us also to consider as teachers, we can make this stressful or not stressful. Okay. What I like and what I wanted to share with the Morningside math is if you notice there are no symbols in there, no equal signs, no addition signs, no subtraction signs. It's just kind of building that pattern memory with students. So if it's the 8 plus 1 equals 9 is what's stressing your students out, there's ways that we can build fluency in other ways. Whew. Okay. I know I breezed over fluency. It's super important, but you can listen to Dr. Ponce if you want on that. He'll dive into that. So if you have questions, feel free to email me. Feel free to email the folks at Patton. They are a wealth of information as well. But I'm going to take the last 2 minutes and address questions in the chat. Okay. Hate them. I got a lot of hate there. That's fine. You know what? It's funny. So I have 2 kids and they're very different. And my youngest, my oldest is kind of right around the corner, potentially listening in, but I'm going to talk about my youngest right now. My youngest, the timing stresses him out. He had something on, it was on the computer and it went from green to yellow to red when he was running out of time. And know what? He spent 0 attention on the math facts that he had to do and all the attention on that timer. Once it turned yellow, he stressed out. So that's, I knew you were talking about, I knew you were talking about the time drills. That's fine. So that stressed him out. Okay. He wasn't working math facts. I give him a paper with math facts and I say, just do this for a minute. He's fine. Okay. With my undergrad students, I gave them a math fact fluency test for a minute. One of the papers, one of the directions, just like, hey, we're just spending a minute working on this because I don't want to spend all class time, but it's important. We're just going to spend a minute, do your best. It doesn't matter. Just do your best. The other one was like, this is a test. You need to do your best. You only have a minute. You have to do as many as you can in a minute. And then I kind of assessed their stress levels. And you can imagine which group was stressed. It was the group that I was like, you need to do your best. You only have a minute. The other one was like, well, that was fine. So we as teachers can kind of control some elements of how we're addressing this. There's lots of different ways to assess facts and to provide practice for math facts. So it is super important. I see it in my own kids. I see it in students. I see it with teachers in classrooms that I work with. But there are different ways that we can address fluency as well.